Yeah, thank you. Hi, everyone. My name is Qian. I'm a grad student from Chicago. Today, I'm be happy to talk about our work titled Constant Overhead for Tolerant Quantum Computation with Reconfigurable Atom Arrays. So this is a collaborative work between with Harvard University, Arizona, Caltech, and QEra. So to start, we know that we have to find against noise and decoherence to enter the quantum realm from our classical world. Although we are already starting to explore new science and technologies with our NISQ machines, there's still a long way to go to really enter the useful quantum regime. In particular, it's well to believe that we would have to further cross the river of error correction and finally enter the fortress of fault tolerance. So more concretely, if you look at this diagram in terms of number of qubits and the areas of physical devices, again, we are roughly at this NISQ regime with a few hundred qubits and a 10 to minus 3 physical arrays. However, the paradigmatic fault tolerance schemes, such as those based on the surface code, are much more demanding. In particular, it really requires like millions of qubits in order to implement your favorite fault tolerant logical algorithms. So clearly, there's a huge gap between where we are and what's ultimately required by fault tolerance. So the question is therefore, how can we bridge this gap? So to answer this question, we'll first have to understand better why there's a gap. So one of the primary reasons is that the leading quantum mechanical codes, such as the topological ones, come with a very large space overhead. So namely, we need many physical qubits in order to get one logic qubits. So if you look at this 2D array of a surface code, here I'm showing, I'm representing, so I'm using these orange circles to represent the data qubits, the red squares and the blue diamonds to represent the Z and X check qubits, respectively. And to make sure everyone is on the same page, so the simplest way of doing error correction is to entangling these check qubits with your data qubits by applying some entangling gates along these edges, and then you measure the check qubits to get the error syndromes, and then you do the decoding. So here I'm using a standard NKD notation to denote a quantum code that has like n physical qubits, k logic qubits, and a distance d, which roughly characterize how many errors this code can correct. So for instance, in the case of a surface code, we always have one logic qubit whose logic operator spans across the entire lattice. And here the distance is given by the weight of its logic operator and therefore the length of the lattice. So in this case, to make the code more powerful, we would have to increase the size of the lattice. However, because we always has one logic qubit encoded, then the encoding rate defined as the ratio between this k and n will keep decreasing. And equivalently, the so-called overhead, defined as inverse of the encoding rate, will keep increasing as the lattice size grows. And in particular, it's believed that a distance 30 is required to implement like large quantum algorithms. And in this case, the overhead becomes enormous and really need about 1,000 physical qubits to just get one single logic qubit. It turns out that this overhead of the code is fundamentally limited by the connectivity. In particular, it's been showing that like for any 2D local quantum codes, like the k times d square is always upper bounded by k, and this upper bound is actually saturated by surface code. In other words, there's no code that can perform better than surface code in 2 dimensions. Therefore, you have to introduce some non-local connection for your qubits to boost the performance of the code. A simple example is by introducing some periodic boundary condition across this lattice, you now get a toric code that now encode 2 logic qubits instead. And furthermore, recently people have shown that if you further relax the connectivity of your code, you can actually end up with the so-called QRDPC codes that can feature very high encoding rates. And ideally, we'll have a code that has a number of logic qubits that scale linearly with the number of physical qubits, and therefore can get a constant encoding rate and therefore a constant overhead, even if we scale up the system. So, however, there are significant challenges associated with these QRDPC codes. In particular, although they are beautiful, mathematical, abstract, they don't seem to be practical, at least for a while. So one of the reasons is that, as shown in this graph, it requires non-local and very complicated connection between these qubits. And as shown in this paper by Delphos, if we only had 2D local connectivity in the lab, which is usually the case, then you cannot implement the codes because you cannot find any thresholds. What's more, a lot of these codes tend to have large code size in order to have a better performance than the surface code. And also, they tend to have lower threshold than the surface code. For instance, although in this Tremblay paper, this successfully demonstrated qubit saving by using some QRDPC code compared to the surface code, this can only be demonstrated in the very large code size regime, say with tens of thousands of physical qubits, and at very low physical areas, about 10 to the minus 4. So clearly, these numbers are not in the practical regime yet. Another question is that so far we have focused on the memory level. However, it's not really clear if the lower head of the QRT-PC code can be maintained if we try to use them for fault-tolerant quantum computation. So to address these challenges in this work, we proposed a concrete implementation of some interesting QRT-PC codes in the reconfigurable atomic platform. So such a platform features not only half-fidelity single qubit and 2 qubit gates, but what's more importantly, it also features a long-range connectivity between these qubits. So more specifically, we can implement some long-range entanglement gate between distance pair of qubits by coherently moving them, bringing them together, and then applying some local Reber gates. However, it's worth to know that such like long-range connectivity is still limited because it's still better to use global control than individual addressing at the moment. Nevertheless, in our work, we show that such limited long-range connectivity actually already suffices for implementing many interesting QRT-PC codes if we can carefully explore their code structures. What's more, by designing some fault-tolerant circuit-level fault-tolerant protocols and a realistic noise model, we can bring a lot of these codes readily implementable in the lab. And finally, we show that we can use these QRT-PC codes not only for quantum memory, but also for fault-tolerant quantum computations. And we show that our constructions naturally lead to a new quantum computer architecture based on the QRT-PC codes, which is very different from the standard ones using the surface code. Okay, so let's get started by convincing you that so it's indeed promising to implement some of these interesting QRT-based codes in practice. So a key element here is the efficient implementation of some QRT-based codes that has a so-called product structure. And we will show that because of this product structure, we can efficiently implement this codes using only global atom rearrangement, which is compatible with the existing hardware. A representative example of this product codes is the so-called hypergraph protocols, or HGP codes for short. So we can understand these codes by simply reviewing the basics of surface code. So everyone knows that surface code can be described topologically by tiling some underlying manifold. However, there's also a very simple algebraic description of this codes simply by taking the product of two classical codes. So here, I'm representing each of the classical codes as a bipartite graph, where the circles represents the classical bits and the squares represent the classical checks. So here we have the two 1D chains simply because we are using the 1D repetition code. And then we obtain the quantum bits, the qubits, by taking the product of a yellow circle and a blue circle, or a yellow square and a blue square. And then we get the quantum z-check by taking product of a yellow square and a blue circle. And similarly, the z-check as a product of a yellow circle and a blue square. And then next, we assign all those horizontal connectivity for all those different columns to be the same as the vertical code. And then similarly, we assign the horizontal connectivity for all these different rows to be the same as this horizontal code. And then by doing so, we recover the surface code. Importantly, we can infer the parameter of these quantum codes pretty much by just looking at the parameter of the classical codes. In particular, the reason we have a very sparse quantum code that only encodes one logic qubits is really because we're using a very sparse repetition code that encodes only one classical bits. Therefore, a natural way to improve this code is to improve the classical codes that we use. In particular, if we can now use a very dense classical code that encodes a linear number of classical bits, then we can end up with a very dense quantum code that encodes a linear number of quantum bits. And therefore, we get the code with a constant encoding rate. The price we will pay is, of course, we now have like 2D not local connectivity. This is essentially because we are using classical code that has like not local 1D connectivity. Nevertheless, it still have this product structure, meaning that like all those horizontal connections is the same across all the different rows, and all the vertical connection is the same across all the different columns. And we show that because of this product structure, we can construct an efficient syndrome extraction circuit using only row and column permutation, which is mostly compatible with the visual atom array platform. As an example, to implement all these horizontal connections associated with this horizontal edge, we can just move this column close to this boundary column and then apply a global Reber pulses and then bring it back. So in practice, there might be many edges associated with this horizontal code. And fortunately, because this graph has a bounded degree, then we can color these edges with a constant number of colors, such that each type of edges have disjoint support, such that we can actually implement the same type of edges in parallel. So at the end of the day, we can implement all these horizontal connections with a constant layer of parallel permutation of the columns. So the example, here's animation. So here's animation of a full sequence of permutations required to implement a concrete HTTP code. So I want to note that this is actually one of the most natural operations you can do for the atom, because you can imagine that these atoms are actually trapped by 2D grid of lasers, and this permutation simply corresponds to reshuffling of some of the laser beams. And in fact, similar permutations have been demonstrated by recent work at Harvard. I hope you attended Dolev's wonderful talk in this morning. If not, I would recommend to go back and check it. And then, so such a syndrome extraction circuit is also fault tolerant in the following aspects. So first, each of the qubits will undergo approximately constant error rate per co-cycle. So if you look at each of the qubits, it's touched only by a constant number of gates because it's called LDPC. In addition, however, there are some ordinary errors associated with this atom rearrangement that could grow the system size. But fortunately, we show that under realistic parameters, this ordinary errors is always negligible compared to the gate errors, and therefore we can still effectively get a constant error rate. And this is also the underlying reason we can observe some threshold behavior later on. Okay, and also next, as shown in the recent work, the circuits also preserve the distance, effective distance of the code, even under the fault tolerant circuit level noise. So which means that it actually can keep the errors under control. It can limit the error propagation. Furthermore, although we are using the HTTP codes example, these circuits can actually readily generalizable to other QID-based codes that has this product structure, such as the leaf protocols or balanced protocols, etc. Okay, so with this efficient implementation, we can now use this interesting, exciting QID-based codes as our quantum memory. So in addition to the HTTP codes that we considered before, we also consider these leaf protocols, which can be viewed as the symmetry reduction of these HTTP codes. And interestingly, these codes can have even higher encoding rates, over 10%. And then, so when considering the realistic circuit level noise model in the atom array platform, we find we can significantly boost the performance of these codes by using this space-time decoding idea, which now treats the entire circuits as a giant space-time code and do the decoding over this space-time code. And then what's more, both of these codes can support the so-called single-shot decoding, which means that a single code cycle actually suffices for implement for fault tolerance. So this is in contrast with the service code where you have to repeat your syndrome extraction D rounds. So this means that these codes can also have lower temporal overhead, at least in the memory level. Although that the single shot suffices to give you a threshold, in practice we'll find that we can further improve the performance by repeating more but a constant number of code cycles. Okay, and then putting these elements together, we can get a high threshold, about 0.6% for both of these codes, which is already pretty close to the surface code. And we can also obtain very low logical failure rate at the realistic failure carry is about 10⁻³ And then with this estimation, we can now estimate the number of failure qubits required for these QRDPC codes in order to reach a target number of logic qubits and the target logic arrays. For instance, if you look at this entry, this means that using these leaf protocols, you will only need less than 3,000 failure qubits to get already almost 200 logic qubits with a 10⁻⁵ logic arrays. Okay, and then to just give you a sense of where we are at the moment, the recent experiment at Harvard demonstrated a 0.5% gate error rate. It's already slightly below the gate threshold. So this really indicates that these codes are not just like abstract things. They're really something that you can implement in your devices, even in the near term. Okay, so finally, I try to convince you that we can not only use this code for quantum memory, but we can also use this code for logical computations. So the major challenge here is that now many of these logic operators have overlapped support. Therefore, it's a bit challenging to perform individual addressing of these logic operators. So to solve this, we actually come up with a scheme. So we're thinking about a scheme that teleported logical information here to a computation block comprising of a bunch of surface code where the logical gates can be applied. More specifically, if, for instance, if we want to apply logical gates on this top right corner logic qubits, then we can just identify the support of this logic operator and pair it with the logic operator with surface code, and then we construct a dedicated ancilla, being the Hubbard product code of these two logic operators. And crucially, because of the structure, this ancilla code has the same Miller logic operators as these two codes involved. And then because of this, we can now implement this measurement-based teleportation circuits that essentially performs the lattice surgery along these similar boundaries. Okay, and then in our paper also prove that such a scheme is photon in the sense that you can preserve the distance while the lattice surgery. And also we can decode this entire procedure by using the same space-time decoding idea, which treat the entire circuit as a giant space-time code. And then by doing this simulation, we observe similar threshold and subthreshold scaling for this QLDPC codes, indicating that we don't really lose much by going from the memory to the logical level. Okay, putting all these elements together, we now actually get a new fault-tolerant quantum computer architecture with a QLDPC-based memory and a quantum version of the CPU, which we call the QPU, that uses the surface code. And then it's also possible to show that we can maintain a constant space overhead, not only for the memory, but also for the entire quantum computer. So the idea is that if suppose we have M surface patches that are paired with a subset of the K logic qubits here, and then for the Hubbard protocols, for example, as long as the M is smaller than square root of K, then we can show that the ancilla qubits are actually sublating in terms of the compared to the memory block, and therefore we still have the constant overhead. Okay, another thing, so of course, there's still a limitation on this M, which translates to a limited number of logical gates you can perform on this QLDPC block at the same time. So however, there's some recent evidence showing that even in this case, for some algorithms, so this mixed architecture still outperforms the standard architecture using only the surface code in terms of not only the space overhead, but also the total space-time volume. Okay, so all these things together indicates that our work brings the QLDPC-based fault-tolerant quantum computing into the practical regimes. Okay, to sum up, so in this work, we consider the practical implementation of certain product QLDPC codes using only global atom rearrangement, which is compatible with today's hardware. And then with this efficient implementation, we can obtain high threshold and constant space overhead quantum memory under circuit level fault-tolerant design. And then we show that we can use this QLDPC code not only for quantum memory, but also for fault-tolerant quantum computation by designing and demonstrating teleportation to topological codes, such as the surface code. And then putting this element together, these things together lead to a new fault-tolerant quantum computer architecture based on the QLDPC codes. Okay, finally, I want to remark that there are also some recent complementary work that together with other work contribute to bring the QLDPC code into practical regimes. In particular, there's also IBM work that also presented at QRP earlier today that shares many similar ideas as our paper, which also came up about the same time as our paper. Okay, with that, I'll conclude my talk and thank our collaborators, Pablo, Chris, Liang, Misha, Hengyun, Dolev, Nathan, Jonathan, and Barney. Thank you.
So we have plenty of time for questions. So just come to the microphone. Go ahead.
Hi, thank you for the wonderful talk. So on your slide where you were quoting the threshold for this code, it had a little footnote that's without idling errors. And at the same time, for example, in trapped ions QCD architecture, there's some evidence that the dephasing during transport becomes dominating source of error. So could you comment on sort of what happens if you add realistic idling noise?
So the threshold we quote here is actually obtained assuming a depolarizing noise model without idling errors. And in fact, if you have idling errors, so actually all this plot actually shows the results with idling errors. And indeed, you can see that actually all the different curves do not cross at exactly the same point. So you don't have exactly a precise threshold when you have the adding errors. But the point is that you only have a small derivation around the threshold value once you added adding errors. So this is already using the existing parameters in the hardware. So basically, take-home message is that without adding errors, you get a pretty high threshold. Without adding errors, you get a very small derivations around the threshold value. You can still observe pretty good threshold value for this practical code sizes.
Thank you.
Hi, thanks for the nice talk. I'm wondering, when you try decoding at the circuit level simulation, is the single shot decoding property a surprise, or does the non-localness of the QLDPC code already implies a single shot decoding property? Thank you.
That's a good question. So, so in general, single shot like LDPC is not enough to imply single shot. You have to have some actual property to guarantee a single shot property. For instance, like you have to require some expanding elements here for the Haber-Graph protocols to be single shot. So in other words, you have to choose a cluster code that's some sort of expanding codes to get this single shot to work.
Thank you.
Hi, thank you for the nice talk. I have a question about your evaluation on the error on the rearrangement.
Yeah.
You're talking about there's a physical error at P0 plus some independent terms for error for rearrangement. You're discussing it's negligible.
Yeah.
By some approximation argument. But if I'm correct, the existing threshold theorem by Gottesman 2013 or Fauci Grosper-Reviel exactly requires this is constant.
Yes.
So if it's growing, I don't know how to prove the threshold, but what's the actual scaling of this? Could you give me more clarification on this?
Yeah, sure. I guess as I comment, if you have some growing ordinary rates, ordinary errors that grow with the system size, then you can not get a threshold, the precise threshold. But the point is that this one is a very slowly growing function. So there are two things. So first, the absolute value of this one is pretty small because the coherence time of the atoms is pretty long. Second, you can make this a slowly like growing function by making by making this rearrangement using constant acceleration. In that case, you can show that with this 2D layout, this one is scale as n to the power 1/4, which is actually a slowly growing function, and therefore it slowly grows with the system size. So we estimate that this one only start to play a role at about a million system size or so. So so before that is still like much smaller than the gate errors.
Okay, if it grows like n to the power 1/4, I'm not sure how to show the threshold, but we can talk later.
Okay.
Yeah.
Thank you for a nice talk. Can you say something about the time overhead when you perform your fault tolerant version of your circuit?
Yeah, that's a very good question. So I think the time overhead will come in two aspects. So first, for any single basically load and store operation, for single that is teleportation operation, you will have to repeat D rounds for this course. So unfortunately, even if you are using code that supports single shot in the memory level, you start to lose this advantage when you do this ladder surgery because of the nature, not the nature, because of the current construction. Therefore, that's one time overhead. It's a bit slow. You have to repeat. I think as another time overhead is that for now, in order to maintain this constant space overhead, we only have a limited logical parallelism. So in the case of for some logic error, in the case of you, so if suppose in some cases you have to use higher some logic algorithm require higher parallelism, then that will also translate to some temporal overhead.
Okay, thank you. Yeah, so I had a question also about decoding. So you mentioned you're using the space-time decoders. So is that also a LDPC code that you end up with? And what algorithm are you using?
Sorry, could you?
Is this the space? You said you're mapping to the space-time code. Is the space-time code?
Mm-hmm.
It's not. Is it also LDPC in this circuit?
Yes, the space-time code also LDPC.
And then what decoder you're?
We're using the more like a standard belief propagation plus other statistic decoding. But I guess I want to emphasize that actually in most cases we're actually just using the BP because like we only use BPUSD for the final round of perfect measurement.
Okay, thank you. Any more questions? Not, let's thank the speaker again.